Well, welcome everybody. This is Society for Industrial and Math Activity Group on Geosciences webinar series. This is our second one, and we're very pleased to have Professor Beatrice Riviere from Rice University join us for this one. Just before I let her speak, I'm going to just give a couple of brief announcements about our activity group. So, first of all, last talk that we had, or the first one in the series from October, it has been posted on a YouTube website, SciAm YouTube website. So you can either search for SciAm YouTube website or find it, or I can also later provide this link. The announcements are made using SciAm Engage that has much more than announcements from our activity group. So I would like everybody to visit SciAm Engage and see all of the information posted. And specifically, I'm not going to go into details. We're really just one of the activity groups, so you can find much more on that website. But I would like to point out that for our activity group and SciAm in general, especially if you're a student, there's a way for you to get a free membership with SciAm. And I think you should strongly consider that if you're a student, or if you know of a student, you should motivate them to join, specifically because there are both possibility for them to get engaged early on in their career in student chapters. And I think our speaker today is in charge or the president of the Texas-Louisiana chapter, if I'm not mistaken, right, Beatrice? Yes. So if you have any questions, feel free to ask about that. And also there is a lot of career-related postings, including preparations for interviews, and so those things might be very useful for students. Our next conference is in June 2023, and I'm going to still keep you on your toes. We're still not allowed to say where is it going to be. So stay tuned, and hopefully by next time we're going to have a signed agreement that will allow us to announce. So this new webinar series is brought to you by SciAg officers, Professor Inga Bear, Professor Vladimir Drushkin, myself. By the way, my name is Masha Pradanovic. I typically start talking without introducing myself, and Professor Chris Keys. They're all actually hidden as panelists on this webinar, so that you might not necessarily hear them, but they are around and present during this talk. I posted our information should you want to make suggestions, provide feedback in any form. You can also simply find us online. There's no need for you to note. Our information should be easily available. And without further ado, I would like to introduce our speaker. It is extremely difficult to summarize all of the things that Professor Riviere has done. She's a professor of computational applied mathematics at Rice University. She also directs computational optimization and modeling of porous media group there. And you can find a lot of very cool stuff on her website if you search for it. She has published 120 plus publications, and I say plus because I think that count that I got from the website is actually from 2019, so there's many more. Then, she has a highly cited book on discontinuous Galerkin methods, and there's a lot of work done in general porous media, both in energy and environmental applications, but also in biomedical applications, so sort of the span of applications of porous media. She's very involved in SciAm. She's SciAm Fellow, which is one of the highest regards that you could get from SciAm, and she's previous chair of this activity group. And that's really just starts the list of all of the things she's been doing from SciAm. So I'm not going to go on that. I will simply let her give a talk. Now, before we proceed with the talk, I would just like a little bit of housekeeping. There's Q&A, which is what I would like you to use for asking questions. You can also raise your hand to ask a question. And if you use chat, you can simply use chat to be social and say hi. So feel free to do that. This is a relatively small group, so if you would like to be moved to the panelist side, so you can simply unmute yourself and discuss at the end of this, we can definitely do that too, in which case we don't necessarily need Q&A. Whatever you're comfortable with, please let us know. And without further ado, I'm going to stop sharing my slides and let Professor Riviere do that.
Okay, so
here we go. We see them.
Can you see the slides?
Yes. Yes.
Okay, very good. Okay, well, thank you so much, Masha, for this kind introduction. And I would like to thank you and the other officers of the activity group for the invitation. I think it's a great initiative that you guys are doing. And I do hope that it will continue for a long time, even post-COVID, right?
Right.
So I'm very happy to be here and to share some of the work that my group has done in modeling porous media flow. And I will, here's a brief outline. So I will talk about these phase field methods for two-phase flow in the porous media at the pore scale. And really the focus of this talk is to show some recent advances in the numerical algorithm. So looking at what we did for the time and space discretization for the case of variable density. So densities of the two phases are not equal. And we are going to show that the phase indicator will satisfy the physical bound. So we are going to have bound preserving solutions. I'm going to show some simulation in microstructures and in digital rocks. So we are looking at direct numerical simulations. This means that the pore space will be given to us, and the pore space, which is on this figure here, it's a sample of a rock that has been a CT scan, and by using 3D imaging reconstruction, we can see the gray area, which is a pore space, so the void space, which is a set of voxels. And what is not seen in white are the solid grain rocks. So we are interested in modeling multi-phase flow, multi-component in this connected pore space. So we're going to take our 3D image and pre-process it so that only the connected pore space remain. So the methodology that we have chosen for this direct numerical simulation are based on the a solution of coupled mass balance equation with the incompressible Navier-Stokes equation. And the mass balance equation come from the phase field methods, where what we would obtain at the end is a Cahn-Hilliard tap system. We actually have what we call the advective Cahn-Hilliard because we're going to have a coupled flow and mass balance equation. So we decided to use the phase field method because they are grounded in thermodynamics, and they are basically using the fact that for the total energy of the system, for a closed system, we have the dissipation of the total energy. So, but there are many other approaches, and pore network modeling, lattice Boltzmanns, and many others. And there is a nice survey by Merkin and Tartakovsky that appears in 2009, where basically we have we can show that describe all the different positive and negative features of each of these methods. So, but independently of the particular method that you choose, when we try to do pore-scale modeling numerically, we all have the same challenges to address. And one of the big questions that we think about is, how is the model, how is the computer model handling the motion of the contact line? Do we have to track that? Is it moving automatically by diffusion process, like it is in the phase field method. So another one is how much roughness of the pore surface can we model? In some cases, if we have a very smooth reconstruction, a smooth surface, maybe it's not realistic enough, right? It's a matter of how much information and how far in the scale we want to go. And also for mixed weight system, we're going to have different weightabilities in different places of the pore space. Another big one for a numerical method is the choice of the boundary conditions. So when it comes to the size of the computational domain, that is more a question of access to large computational resources, like access to clusters of GPU or CPU clusters. So and for direct numerical simulation in particular, that is a big issue because the field of view may be restricted. We may not be able, due to limited access to large cluster, we may not be able to solve problems on a field of view that is comparable to what experimentalists are looking at. So, and then in particular in the phase field model that we are looking at, the Capri number plays a big role. And I will say a few more words on that towards the end of the talk. But for this solving this coupled system of PDEs, as the Capri number goes to zero, becomes smaller and smaller, we obtain stiffer numerical methods, numerical system to solve, and therefore we need to really think about efficient solvers to solve these stiff systems. So to dive a little bit more into the phase field method, so they come from the seminal work of Cahn and Hilliard in their series of papers in the 50s and 60s. So they were interested in modeling phase separation in a binary metallic alloys. And in this case, the unknown of the Cahn-Hilliard equation would be what I call a phase indicator. So we also call it an order parameter. So this order parameter will take two constant value. So it will take a constant value in phase A, and if we have another phase B, it will take another constant value. Now, depending on what you choose to represent, what you choose for the C, the definition of C, you could have 0 or 1, or you could have +1 and -1. So here we assume that C represents the difference of mass fraction. So we're going to have a +1 in one phase and -1 in the other phase. And one of I think the good feature of this phase field method is because we have a diffuse interface, the contact line is actually moving naturally. We don't need to track it. We don't need to do anything special for it to move along the solid boundaries. And numerically, so mathematically, the way you obtain the motion of the contact line is when we go through the rational derivation of the Helmholtz free energy, obtain a non-homogeneous Neumann boundary condition. And I will show that in a couple of slides. So this is a schematic showing you what I mean by this constant value. So if we have two solid phase and we have some fluid inside, we're going to have the order parameter taking a constant value, let's say +1, -1 in the other phase, and then it's going to continuously vary from -1 to +1. So of course, one of the questions is how big is this interface, right? Because we want it to be as small as possible to be as accurate, but this is going to have an effect in how computationally feasible we can solve the system. So here we really show for the schematic, we zoom out the interface. The interface will not be that big, and it will be of the order of the grid size, in fact. And so the location of the interface really relates to this chemical energy density. And so this in this case, I'm showing you the Ginzburg-Landau chemical energy density potential, and the values, the minima of that chemical energy density corresponds to the bulk states. So this mass balance equation takes the following form. So we have a time derivative term, then we have the diffusive term where mu denotes the chemical potential, and mu is basically the Marshall derivative of that Helmholtz free energy. And so mu will be given as a derivative of the chemical energy density minus a term, the Laplace operator applied to the other parameter. And Cahn here, the Cn is a Cahn number, which is of the order of the grid size. So we have a coupling of this mass balance equation with the incompressible Navier-Stokes equation, which are given below here, through this advective term here and through the right-hand side. So basically, we have nonlinear reactive reaction term, we have the diffusion term, the gradient of the pressure, and the coupling term here is what is going to, so if we start with a system that is at rest, the fact that the initial configuration is not at equilibrium is going to make this non-zero, and that would create a velocity field that eventually would lead the whole system to reach equilibrium configuration. So this system of equations are written in a non-dimensional form. So that's why we have this Peclet number, Reynolds number, the Capri number, which basically is a ratio of the viscous. So which basically will give us, as the Capri number goes to 0, this means that the Capri forces will dominate. And then the Cahn number we talked about. So in fact, if we really want to do a more realistic model, we're going to, instead of having a Laplace operator to the chemical potential in the mass balance equation, we should have a mobility that is degenerate. So we're going to have a div grad operator, and this mobility here should be 0 in the bulk phase and should be non-zero in the interface. So while we have done some simulations, some simple problems, simple test problem, it's actually make it very difficult, computationally challenging to solve, because we're losing coercivity if we have a degeneracy in the coefficient. So in what I'm going to show in the rest of the talk, we are simply assuming constant mobility. And so one of the contribution is to have a density that is varying in the interface. So we assuming that we have a constant density for the phase A, constant density for the phase B, we are using the linear mixing rule. The model, we could use any other type of mixing rule. We have taken this one, we have chosen this one. And so let me describe a little bit of the boundary conditions. So for closed system, the mass is conserved, the energy dissipate, and this means that we have a homogeneous Neumann boundary condition for the chemical potential. Now, I talked somewhat about the contact angle and this non-homogeneous Neumann boundary condition for the other parameter, and it is written here. So this is again obtained by applying the Marshall derivative to the Helmholtz free energy. And so we have tested this, we have validated this boundary condition, and basically just to say what it is. So you can see that it is a nonlinear boundary condition because it involves the unknowns in the right-hand side. Theta would be the contact angle, and we have this parameter delta, which I can say is a fudge factor. So why do we need to have a fudge factor delta? Is because we are directly solving on these 3D images, and we're going to have this jaggedness that is due to the resolution of the scanner. So in order to eliminate some of these, to minimize the effects of the jaggedness due to the resolution of the scanner, we have introduced a delta, and we have a paper on explaining how we can compute the delta. So this delta is computed for each solid phase, and it is stored. It's computed once, and it's stored in a file, so we can do a quick lookup table to find the right delta for a given phase. So one way we validated this delta is by comparing our numerical simulation with experimental setup. So, and this is collaboration with Imperial College of London. And so the figures to the left shows the image from the experiment of a ganglion, which is a darker color of an old ganglion, and then the white color here corresponds to the solid grains, and the gray area would be the light gray would be the pore space. So this is obtained by experiment, and this is what we obtained with our simulation. Now, we are solving only the Cahn-Hilliard equation here. This is not coupling with the Navier-Stokes. We started with a cubic shape ganglion, and we let the system evolve to equilibrium. And we were happy that we would then compute. We would, that first of all, using the eyeball norm, that we have a match, and we can also compute the contact angle, and we have a good comparison with what was observed experimentally. So to continue on the boundary condition for the velocity, for the momentum equation, we're going to assume no slip condition on the rock surface. And again, that we could argue that maybe this is not the best boundary condition. I mean, you could have maybe a layer, a transition layer very near the wall and add, some additional nonlinear terms. But this is what we have used. For the inflow boundary condition, we're going to use Dirichlet boundary condition. And then for the outflow, we're going to use this do nothing boundary condition, which is a type of attraction boundary condition. So now what can we prove about this numerical, PDEs? So there are some a good amount of work on the discretization of the coupled Cahn-Hilliard and Navier-Stokes equation, and they utilize different numerical methods: finite element, mixed finite element, discontinuous Galerkin. So I'm listing a few of the works here. So the difference between the different papers is, besides that you may use different method, is that you could use a fully implicit where you solve both the mass and the flow equation together, or you do a sequential, which would be cheaper because you kind of decoupled and you obtain smaller systems. You could also use different chemical energy density, and again, you could also use different coupling terms. So at the PD level, these coupling terms are equivalent, but at the discrete level, they will not be equivalent. Now, one common feature of the different papers, theoretical papers, is that they assume equal densities and neutral walls. So the challenge in this for doing the error analysis is that to derive optimal a priori error estimates, for instance, it would be great if we can show that the discrete approximation of the order parameter is bounded in L infinity. So in general, in 3D, we don't have this. But one way to circumvent this problem is to assume additional restriction or smoothness restriction on the chemical energy density. And in particular, so if we write the chemical energy density as a sum of a convex part that I denote by plus, V plus, C plus, and concave part that I denoted by psi minus. So we're going to assume that the derivative of the convex part and the derivative of the concave part are Lipschitz continuous. So if we do that, then we can prove optimal error estimates. Now, is that realistic? So if we have the Ginzburg-Lambda potential here, which is drawn in red, so what we need to do is we need to regularize it, and we need to extend it in a smooth way so that we have a global C2 function. So we can do that for some of this chemical energy density. This one here is the logarithmic potential, which is another function that one could use. So for the time, so now I'm going to go more into explaining what type of discretization we have used. So we, of course, use the convex-concave splitting introduced by Ayer in the 90s. This is very important because it allows us to obtain a scheme that can be energy dissipative, in general, right? So, and for the Cahn-Hilliard equation, so we are basically using a first order in time backward order, and we treat the convex part implicitly and the concave part explicitly. So as you can see, we're still going to get a nonlinear system because of the convex part, and we're going to do an inexact Newton to solve the equation. So once we know the other parameter, we can plug that into our mixing rule and we obtain our density. So the Navier-Stokes equation part is a little bit more complicated because we decided to use an operator splitting. And the reason we decided to use an operator splitting is because it is known that it is more computationally efficient if we have for large scale computing. Okay, so we are going to solve we're going to solve for two velocities, and we're going to solve for potential denoted by phi and the pressure. So the next slide shows you the 3 steps for this operator splitting, which is what I denote here. I call this a standard way because this is used in the literature for solving the time-dependent incompressible Navier-Stokes. So here we simply modified it because we have the density in front of it. But so basically, don't want to go too much into the detail, just emphasize a couple of points here. So we solved the velocity Vn, assuming that we know the potential and the pressure, the previous time step. Then we create a new potential by solving this elliptic equation. And then once we have the Vn and the Phi, we can use that to obtain updated pressure and velocity. And the velocity that we use in the Cahn-Hilliard equation will be the UN here. So why is this operator splitting created? So why do we have 2 velocities? So the velocity Vn will satisfy the boundary condition, whereas the velocity UN will satisfy the divergence condition, the incompressibility condition in a discrete sense. Now, this the thing that is not super efficient here computationally is that at each time step, the density varies, right? Because you have the phase that propagate through the pore space. So at each time step, we're going to build to assemble this matrix. So we're proposing a more efficient way to deal with solving the Poisson problem, so that we're going to have the Laplace operator here. And because we modified this equation automatically, we will have to change the update of the velocity. So this is the algorithm that we propose and we have implemented. So first we need to define a reference density, which is a minimum of the two-phase density. This is constant. And then what you do, you basically transform that div grad operator in the following way. So now we have a matrix, a left-hand side that can be, assembled once, and we can reuse it at every time step. And the only thing that we need to worry is to create a new right-hand side at every time step, okay? So, and then this is how, because we have a different right-hand side, this goes into here and we modify the velocity. Okay, so for the spatial discretization, we are going to use a discontinuous polynomial approximation. These are the known as the interior penalty discontinuous Galerkin method, and for the convection term, we're going to use upwind. I'm going to show you some simulation where we either use piecewise linears or piecewise quadratic in each voxel set. So of course, we know that like any other numerical method, we have pros and cons. And the pros of using this discontinuous Galerkin method or any finite element method is that these methods are known to be stable, and we can prove for model problems that they are convergent with high accuracy. Because we have this discontinuity in the approximation space, we also have local mass conservation, and we also have a sharp front because of the, I mean, so DG is known to have very small amount of numerical diffusion. So this means that the front will be sharp. So this means that in this interface, will be well resolved. Now, what are the negative features of the discontinuous Galerkin discretization is that there is no maximum principle. We normally, I mean, in general, we cannot prove that we have physical bounds that are satisfied. So this means that while the front might be sharp, you're going to have some overshoot and undershoot right before and after the front, or the interface, near the interface, the diffuse interface. So the other one is that as you increase the polynomial degree, then you're going to have larger and larger systems, and therefore it's going to be more costly to solve. And this means that one really need to worry about developing efficient preconditioners and linear solvers. So we verified our method on the smooth problem, and I just mentioned we have optimal rates, and convergence of the method, and this is just to show you on this slide that indeed we recover the optimal rate. So in this case, we use a piecewise linear, and we look at the error for the order parameter, the velocity. Oh, and there should be the velocity and the pressure in L2, and we obtain the rate of 2 as expected. Now, let me show you an example in a simulation in a microstructure. So the resolution in this, so basically we have a thin slice, and we have about 400 by 400 in the X and Y direction, and we attach to this microstructure a buffer. The buffer allows us to impose the inflow boundary condition much more easily, and it kind of matches what is done in experimental setup. So we are going to assume non-equal densities. This is a ratio of the density. And in this case, we are going to have a wall that is hydrophobic with respect to the phase A. So we're injecting phase A. The microstructure is assumed to be full, to be filled by phase B. So this is what we would obtain using the scheme, the discretization I just talked about. And these are the snapshot of the order parameter. It basically shows you a different time, earlier time, later time in the simulation. It kind of shows you where the phase A, how it propagates through this microstructure, so these connective pores. Now I want to, so you may observe that there are some black regions. So the black regions are the regions where the order parameter violates these physical bounds. So it's going to be above +1 or less than minus -1. Now, so these bounds are violated, but the method is still stable, and it, would give us a good approximation of where the phases are. It's just that, before and after, you may have this violation of the maximum principle. So here's another simulation where now we don't have any, no longer these black regions, right? So in this case, what we have done is we have applied flux and slope limiters to our order parameter at each time step, and we now obtain a similar, so the figures are very similar, except now we have that the order parameter satisfy the physical bounds. So this is the same simulation, but I like to show you these figures because you can see what I mean by the fact that in this case, the phase A just does, so this is like, let's say, all weight structure. So the phase A avoids the solid grains, the walls. And also the other thing that I want to point out is you see how resolved the interface is, right? The diffuse interface, and what I mean about very little numerical diffusion using these techniques is observed here in this setup. Okay, so what is the algorithm with this slope limiter technique? So basically we, at each time step, we first solve the Cahn-Hilliard, the additive Cahn-Hilliard equation. Then we're going to apply two post-processing techniques. So first a flux limiter then a slope limiter. And once we have that, we're going to update the chemical potential. We are going to update the density, compute the density, and then using those to solve the Navier-Stokes equation using our operator splitting technique. So now I want to describe a little bit more detail this flux and slope limiter. So really the flux limiting technique is based on the work done in the 70s by Salezak. And this work has been introduced and used in the work by Kuzmin, Kolb, Frank, Rupp, and Kuzmin. So here's the idea. So the idea of the flux limiter, it's very well suited to this discontinuous hierarchy method because we have discontinuous approximation. So the flux limiter what does it do is really fixes the cell average, so the element-wise average that violate the maximum principle. So for notation, we put a bar to denote the element-wise average, so the cell average of the other parameter. And because of the discontinuous polynomial approximation, you can show that the numerical scheme, the GG scheme, gives you this equation. So the cell average at the time Tn is equal to the cell average at the time Tn minus 1 minus 2 times some flux quantity. Of course, this flux quantity here, they are flux that occur through all the phases of a given element, but they depend on the saturation, they depend on the other parameter at the time Tn, right? So what is the idea? So the idea of, using this equation, we are going to modify the flux. So we're going to construct a sequence of fluxes that will be shown to converge so that when we plug them back into this equation, we're going to have a new cell average that I call it lim, that will satisfy the maximum principle. So if we assume that the cell average at the previous time step is between -1 and +1, then the new cell average would be between -1 and +1. And once we have the new cell average, we just put this back into our approximation to obtain a new approximation that has a good cell average. So, but because your cell average is between +1 and -1, that doesn't mean that your approximation will be +1 and -1 because we're using linears or quadratic, right? So in this case, what we do is we check the cells or the elements where pointwise it is violated, and then we apply a slope limiter. Now, we have chosen the vertex-based slope limiter defined by Kuzmin, but there are multiple slope limiters in the literature, and any slope limiter would work. So in this case, so the idea of a slope limiter is we don't touch the cell average. So this has already been fixed by the flux limiter. And now we play with the magnitude of the gradient. So we have this parameter beta E that we tune so that at every point in the element, we are going to have the maximum principle to be satisfied. So the good thing about this flux and slope limiter, and that's one of the reasons we pick this one, is that we can show, that rigorously we have a proof that if we start with a good approximation at the previous time step, then with the new with this limiting technique, we're going to get a good approximation at the current time step. So so now I'm going to show you some examples. So this is a benchmark problem where we have two droplets that are touching each other, and so initially they're at rest, and so this is phase A is the droplets and surrounding by phase B, and the color green here shows the interface. Okay. And so hopefully you see the movie. So we expect that the equilibrium configuration would be a sphere. And you see that we have a transition regime where you have the two droplets merging, and then they're kind of wobbling until they reach the equilibrium configuration. So these are some snapshots, just in case the movie could not play. But I just want to point out that, we do have an order parameter that does satisfy the physical bounds. This is the profile of the order parameter extracted along a diagonal. And this is at another time step. Okay, so then we did the simulation of two-phase flow in digital rocks. So in this case, we have a resolution of 160 in the X, Y, and Z direction, and we added two buffers, one at the inlet, one at the outlet. And in this case, we are injecting a phase A that will basically now sticks to the wall. So the contact angle is 80. And this is a snapshot of the distribution of the phase, how phase A is in that pore space after 10 pore volume. And we now look at here for the Capri number equal to 1. So for the next couple of slides, I'm going to just change the value of the Capri number. So this is what I just showed. And this is Capri number equal to 10 to the minus 1. So we're going to, as we decrease that Capri number, we understand that the Capri forces will dominate. So we're going to have a different phase distribution, after 10 pore volume. And, this is what this figure tells us here. So again, the legend, so red is phase A, this kind of blue, transparent blue is phase B. And then whenever you see green, you see the interface. So 10 to the minus 2, 10 to the minus 3. Now, this Capri number is quite interesting, and we can have a whole, debate about the Capri number and talk about it for several hours. So one of the questions that we were interested is, how do I know at some point where Capri forces dominate and where viscous forces dominate? Because we're solving this equation in a non-dimensional fashion. And for us, I mean, it was not clear to us how this Capri number in our model relates to the Capri number shown, seen in experiments, which we know in experiments, the Capri number are much smaller, 10 to the minus 5, 10 to the minus 6. in the literature, we have papers on what that means, and you have different value, different range if you're looking at microscopic or macroscopic values of Capri number, if you have large ganglion and so on. But for us, we are really wanted to see, where we were in that regime, right? So, and what we did, we computed the desaturation curve. So we injected 40 pore volume for each of the Capri number, and we computed the residual saturation. So so basically the amount of phase that remained trapped that did not move. And so this is Capri number equal to 1, then it goes down to about 10 to the minus 2. And you see that the residual saturation is more or less constant. And then as the Capri number goes further down, we have a jump, and then we have a higher residual saturation. So these type of curves are well known in the literature. And for us, we were at least happy to see that we do observe a similar type of trend. We do have a jump in the residual saturation. And for us, it means that in this region, so I'm going to have the region where Capri forces dominate. And in that part, the viscous forces dominate. So that transition region it's of the order, it's between 4, 10 to the minus 3 to 10 to the minus 2. Now, honestly, I think while we were happy to see that, it's still, I think, I guess it makes us ask us more questions, right, than give more answers. But so I think this is a preliminary, and we should do more simulation. And in particular, one thing that we want to do is run this on larger size rocks. So one thing that I did not talk at all about is this energy dissipation, which is a motivation why we use this phase field method. So I'm showing you here the law for the dissipation of energy. So the derivative of the total energy is negative. And the total energy has the kinetic energy, the Helmholtz energy in the bulk and in the diffuse interface, and also the contribution to the energy. This is what we call the surface energy. So it's a contribution to the energy of the interaction of the fluids with the solid walls. And it involves the interfacial tension between the two fluids, the surface tension between phase A and the solid. We have the contact angle theta. Here's our fudge factor delta. So we can show that for the PDE model with equal densities, so rho A equal to rho B, that we have the following energy dissipation. And also, depending of the discretization and numerical method that you use, in some papers, in some cases, you could also have a similar energy dissipation law at the discrete level, okay? And this is just a figure that shows that, yes, the energy dissipates. And this goes back to the problem of the two droplets that are merging. And just focusing on the black line, which is the curve showing you the total energy. So it goes down. But for non-equal densities, the PDE model that I've shown you is not energy dissipative, okay? So, and there are in the literature, not a lot of papers, but there are a few papers that introduce and formulate models that are much more complicated to try to address this problem. What we have done is we have followed the work of Abels, Garke, Grun, where to make the previous PDE model energy dissipative, we need to add one term to the momentum equation. And this is a term in red. So if you do that, now at the PDE level, you can go through your proof and you can show that the derivative of the total energy will be negative. So you have energy dissipation. So what is this term? So it involves, of course, first of all, we observe that if you have equal density, that term vanishes. And if you have non-equal densities, it's basically a scalar times the gradient of the chemical potential, right? So what we did is we went ahead and, oops, went too fast. We implemented this term. We discretized it and added to our software. And I'm showing you this curve of the total energy for when we add this term for non-equal densities for the benchmark problem, which is known as spinodal decomposition. To make it a little bit more interesting, we did the spinodal decomposition in a torus. So initially we have a random distribution of the phases. That's why you see blue and red. And then as the time evolves, you have the phase each, so the phases will basically get together and we're going to have this, eventually we're going to have this configuration. This will be the equilibrium configuration. So I think I maybe should conclude. And so basically, as a conclusion, I want to point out some of the open questions. So for instance, theoretically, the convergence analysis of numerical scheme for the couple Cahn-Hilliard and Navier-Stokes equation, while there are some works, they are all valid. They are all for the case of neutral walls and equal density. So it would be of interest to see, can we do something theoretically in the case of non-neutral walls and variable density? I'm not aware of any, but if a person in the audience know of such a work, please let me know. I'm very interested in that. And also, so the thing about, I've shown the phase field, the simulation using of phase field method. And I'd mentioned that the reason we pick is that because they're based on thermodynamical and conservation laws. But in fact, this framework allows us to add more physics in a relatively simple manner. And what I mean by that, and we have run simulation where we have non-Newtonian flows. The viscosity of the fluid will depend on just the shear rate or something. So relatively easy to implement it, to write the model, to discretize it, and to implement it. We also have, because we have this contact angle as a boundary condition, it's also relatively easy to have a mixed wet system and to do simulation on this problem. Now, the cons is that all of this is going to be very expensive, and especially if we increase the size of the field of view, right, of the rock. And this means that, of course, it's imperative that one run this simulation on large clusters. So currently my group is looking at adding a little more physics, increasing the physics. So we are looking at adding surfactant, and we're also looking at partially miscible flows. And so I want to acknowledge my collaborators. So I'm very lucky to work with excellent team of collaborators, and starting by thanking Chen Liu, who is really the main driver of the work that I presented today. So Chen was my former PhD student, and he's now doing a postdoc at Purdue. And then, so going through the names, so Walter Chapman, Florian Frank, Christopher Thiel, Lu Lin, Deep Ray have all worked on with me on this understanding and modeling these pore-scale flows. And I would also like to acknowledge the collaborators from Shell, so Omer Alpak, Detlef Hall, Stefan Berg. Very grateful for the many useful conversation we've had on working on this project. So the funding has come from Shell, and also I would like to acknowledge funding from NSF. And I have access to several clusters, and more recently to clusters through an EXCEED grant. So I'll take any questions.
Excellent, thank you very much. So we already have a number of questions. And I'm going to ask a question that was initially early on posed in the chat, and I'm gonna, Amir, I'm gonna allow you to talk. But before I should state that if I butcher your name, I apologize. So Amir Jahanbakhsh asked if the fudge factor can basically contribute to inclusion of the, or upscaling of the surface roughness in the model.
Yes, the answer is yes.
So,
yes,
but
so we, you know, so the fudge factor, so the way we actually came around to add this fudge factor coming from the opposite direction. We wanted to remove the roughness surface because of this, because for us it was a numerical artifact coming from the resolution of the scanner. However, you could, if there's a way to validate, right? The thing is to validate this fudge factor the way we build it. You could go back in the other direction and try to see if one could use the same technique to incorporate the roughness, but the physical roughness, right? I was not sure that was okay. Yeah. So in brief, the question is yes, but we have not done it. So
yeah, that was my initial joke in the thing, that you should actually call it a surface roughness upscaling factor. So that prompted the question. All right, Arsalan, if you're there, I'm going to ask you a question, but I'm going to unmute you or allow you to talk if you want to follow up. So the question that we got in Q&A was if you introduced any additional equations for the divergence of velocity values in the discretized domain.
No. I'm not sure I understand the question. Let me go back to the PD model.
Arsalan, you can talk if you can follow up.
Hello, can you hear me?
Yes, you can.
Yeah, I think I joined like, I think 10 minutes late. I'm sorry for that. But when I joined, I mean, you mentioned you've been describing the equations. And I think one part you were mentioning about the divergence in the discretized domain, which I interpreted the fact that the summation of the velocities or the mass should be equal. So I was wondering, did you have any additional equation to make sure that the that divergence on the velocity is 0 on each of the volumes?
So, okay, so I think maybe your question is asking about mass conservation. So mass is conserved. Okay, that's one thing. Now,
Okay.
if your question is, how do we handle the divergence? Now, this is how, basically going back to this operator splitting, that is why you have two velocities. And that is why you have this complicated right-hand side. By this construction, at the PD level, you can show that the divergence of U is 0. But because we are doing this discretely, you're going to have a discrete version of the divergence. And if you compute that divergence, it's going to be small. It's not going to be machine precision, but it's going to be of the order of, I don't know, I honestly don't remember, but very, very small.
Okay, thank you very much.
Mm-hmm.
All right. So next question is, Soren, I'm going to read it out, but I'm going to allow you to talk so you can follow up. Soren Pop is asking if you mentioned optimal error estimates, and he's asking if these are obtained also for the operator splitting approach, like 16, which we are on.
Correct. So we this is work in progress. So the one that I mentioned, the optimal error estimates, are done for the regular non-operator splitting. Now, I do have an excellent PhD student who has tackled this problem, and so his name is Rami and Rami Masri, and he has first obtained the a priori error estimate for just the operator splitting for the time-dependent Navier-Stokes equation. And now we're working at deriving the whole thing with a coupled with Cahn-Hilliard. So stay tuned for that.
Looking forward to it. Thank you very much.
Soren, do you want to ask your second question too? So now that you're
Oh yeah, yes, sure. Thank you very much. And once more, thanks for the great talk. I really learned a lot. The second talk was, I was triggered by your example with the microstructure. And I wonder, is it a way to compare this with some upscaled model? I mean, basically you could homogenize it and yeah. Is it,
Yeah, I think
nobody tried this, or?
I'm not aware, but it's a good idea.
Yeah, okay.
Yeah.
And since I'm the same topic, did you pass, I mean, the diffuse interface parameter to 0? When passing it to 0, you would re-get actually the sharp interface model?
So we did not do that, but yeah, there are some papers that talk about the limit. You know, when you take that diffuse interface parameter epsilon, let's say, and you put it to 0. But in our case, we fix in our simulation our diffuse interface parameter is of the order of h square. Right, that Cahn number, it's a Cahn number square, and Cahn is of the order of h, so it is h square. So we have not tried, we have not tried to make that go to 0 and see what happened.
Thanks a lot.
Sure.
Thanks.
all right. Inga and then Chris, since you're panelists, you can just talk. Or if you want, I can ask your question. But
hi, can you hear me? Oh.
yes.
Thanks. Okay, it might be my dog wants to talk as well. So if you hear it in the background, well, yeah, I was just wondering, you mentioned partially miscible flow. Is this sort of a straightforward extension, or are there some challenges hidden there?
So, okay. So we've been working on that for a couple of years. So I think there are some challenges. So, and the challenges does not really come from, I think the challenges is really come from the model. It doesn't come from the discretization, you know, because we know how to handle that, but from the model point of view, and how do we, okay, so if I try to remember, so we want to show, again, energy dissipation at the PD level and what, you know, things like that. So, yeah.
Yeah, so it's more of a modeling challenge and yeah, solution. Yeah, thanks.
Yeah, sure.
All right. Well, Chris unfortunately had to hop off, and we are at the hour. I would like to throw in one small question, and that is the following about the discretization. So are you keeping the voxelized nature of the original image as discretization?
Yes.
Why? So I think, to me, finite element methods make it possible to actually in the middle of the pore space have larger elements, and closer to the interface or the surface, solid surface, have possibly a finer discretization, which could be beneficial.
Yes, I agree. Mesh adaptivity would really help here. So the constraint of because we developed the software pretty much from scratch, and the constraint of the software is that right now it does not allow for mesh adaptivity.
Okay.
But if I had to redo it again,
right, no,
I would.
It's a non-trivial problem in porous
Mm-hmm.
media. I'm not going to argue that, but I work with methods that are often stuck on the grid that comes from a micro CT. But the level set modeling that I've been doing, as well as lattice Boltzmann, is actually also defined for such grids. But in the problems with the contact angle, you would like to have a refined discretization near the surface, as well as, and you can smooth out the roughness that comes from the staircase effect. That's fine. That can be done. But you need sort of a finer resolution there if you're going to monitor contact angle, and inside of the porous medium, maybe not so much, and there could be some savings there. That's all.
Yeah. So here the methodology is totally amenable and suitable for that. It's a matter of implementation, right? It's a matter. Okay, so
yeah.
That's
and another talented student.
Yes.
Okay.
Exactly.
All right, thank you very much. So unless there are other questions, we can keep this pretty much on time. So I appreciate everybody's time in joining us. This will be posted on SciEm YouTube channel, and I will alert on SciEm Engage website when that is done. Also, you can follow me on LinkedIn if you want to get these announcements. I do actually post them on LinkedIn. So if that's your preferred way of learning about these, please do that.